Hi, I'm Anna Tauke-Pedretti, a program manager here at the Microsystems Technology Office. I joined DARPA in November of 2022 and jumped at the chance to become a part of the innovation at DARPA when presented with the opportunity. I came to DARPA from Sandia National Labs, where I spent 14 years creating and understanding the failures of microsystems for imaging, signal processing, power management, and digital communication. This experience has really colored my perspective, and here at MTO, I'm interested in scaling microsystems in order to enable new capabilities and access to the microsystem community. First, I'd like to share a little bit about my current program portfolio. PIPES is about scaling interconnection between microsystems, breaking the latency, bandwidth, and distance bottlenecks associated there. LUMOS is about adding gain to photonic integrated circuits, allowing for a scaling in the complexity of the circuits, a scaling in the output power of the circuits, and a scaling in the spectral access. And then finally, I have SOAP, which is about scaling phased arrays using innovations in algorithms and hardware and interconnections to distribute the processing across the array. As I look forward to new program ideas, I'm really interested in microsystem scaling. In particular, I'm interested in the areas of photonic scaling, scaling materials manufacturing, and scaling communications. Within photonic scaling, most folks are familiar with Moore's Law, which governs the scaling of the number of transistors on a chip and has been a driving force in today's microelectronics industry. And now 3D integration is allowing for additional scaling in materials and functionality. And DARPA has been investing in this for microelectronics with the Next Generation Microelectronics Manufacturing Program. Integrated photonics has seen the beginnings of similar scaling. In the 1990s, indium phosphide-based photonic integrated circuits showed the integration of multiple components on a similar substrate. And then in the early 2000s, we realized how to harness the silicon microelectronics infrastructure in order to create silicon photonics, which has seen a tremendous enabling of scaling and complexity over the last decade to create more functional circuits. The question now is, what is the pathway to continue scaling these photonic circuits in complexity and density? One answer may be borrowed from microelectronics, and that's moving to the third dimension. Here, three-dimensional circuits can allow for denser active components into more complex circuitry, and it can also allow for the interconnection between multiple chips in order to create more complex photonic microsystems. Another area of interest is material scaling. Silicon-based platforms have benefited from large volumes to drive manufacturing. Here, statistics allow for the rapid innovation of new technologies for silicon manufacturing. However, there continues to be drivers for more diverse material systems beyond silicon in order to enable new optical wavelengths, high power, higher frequencies, and new sensors. As these new materials are identified, a key question is how to rapidly mature their synthesis and processes in order to quickly generate new devices and circuits enabled by their new properties, moving the time from materials discovery to working devices from decades to mere years. I see three important components in realizing this vision. The first is asking the question of how to synthesize these new materials in a universal and scalable way, rapidly producing materials that can be fabricated into devices, and producing these materials in quantities that can be run through fabrication processes. The second is realizing fabrication processes that can be rapidly developed and modified for new materials, creating materials agnostic fabrication. And then the third component is creating real-time in situ metrology that provides not only feedback on physical processes and properties, but on device-level properties. Of particular importance is the ability to understand the properties of the interfaces being formed, because interfaces are what drive overall device performance. And then these three important components need to be interconnected with pathways established to adjust in real time our synthesis and processing of the materials so that we aren't relying on quantities but information to create the highest performance device possible. Finally, another area that is ripe for innovation is scaling communication. Here, I'm not simply talking about scaling the volume of information that's already being explored in programs like DARPA PIPES. Instead, I'm interested in adding new capabilities to the communication between microsystems. Examples may include new ways to do information broadcasting, sharing the same information amongst many nodes with low latency and power, or enabling coherent communication in physically distributed architecture, where nodes are fragile and thus require resiliency. Finally, I would like to ask for your help. Like all things at DARPA, we accomplish nothing without the innovative ideas of our performer base. So I am asking you to please share your concepts that will disrupt fabrication, material synthesis, metrology, information distribution, and photonic circuit scaling. Thank you.